Alright guys, so today's video is going to be all about axial member buckling. This will be section 3.4 of the notes. Let's just define buckling first off. So first off, buckling is this phenomenon that produces sudden lateral deflections in a axial member when it is under compressive loading. Okay, so what we mean by sudden lateral deflections is basically it just kind of all of a sudden bows out. Okay, so just imagine, if you will, that you've got like a thin piece of wire, okay, some type of metal wire, like maybe you've taken a paper clip and straightened it out, so now it's just a piece of straight wire, and you hold that piece of wire in between like two of your fingers, right, between your thumb and your middle finger, and you are kind of pushing those ends together, putting that little piece of wire in compression. Okay, so if you can imagine that you've got this paper clip in the straightened out paper clip between your fingers, and you start pushing on it a little bit, putting it in compression, it will initially resist some load. Okay, you may be only pushing with a couple of pounds worth of force, right? But that paper clip is holding the load. But at some point, when you push those ends together, that paper clip is going to all of a sudden bow out. Okay, that is the point of buckling. That is when that member has buckled. So that sudden lateral deflection is what we call that bowing out of a compression member. Okay, so instinctively, I also want you guys to understand this, that let me get my pen up here. Instinctively, I want you guys to understand that buckling cannot happen in a tension member, right? An axial member that is under tensile loading will not ever experience buckle. You're never going to be able to pull on a cable or pull on a pipe or anything. If it's in tension, it's never going to buckle with that sudden lateral deflection. This is specifically for compressive loads. All right. So now that we've got an idea of just what buckling is, we're going to start calculating what we call the critical load. Now we call the critical load P critical, P sub CR, and this is simply the load, right? This will be in kips or pounds, right? This will be in force. All right, this is not in any kind of stress. This will be pounds or kips or newtons or kilonewtons. This is the load at which a compression member will buckle. Okay, it's a very theoretical equation, and it's based on a lot of partial differential derivations that we're not going to really spend our time in class going over. I don't think it's necessary for you guys to see the derivation of this equation, but what I do want you to understand is that there are compression members out there, right, obviously, and when they are under a compressive load, at some point some compressive force is going to make that member buckle, whether it's a column or a pipe or something. If it's under compression, if it gets to be under enough compression, it's going to buckle at some point, and our job as designers is to figure out what is the load that will buckle that column, and we need to stay under that load, because when a column buckles, it has essentially lost all of its structural integrity. It has failed as a compression member. It is no good after buckling. So we always want to stay below the buckling loads. We do not want our compression members to buckle. So we need to be able to know what this buckling load is, what we call this P critical or the critical load, be able to calculate that force, and so that when we're designing we can stay under it. So there's a couple variables in this P critical equation. Obviously we'll just start off with pi, right? Pi squared is just pi 3.14. E, as we've talked about, is modulus of elasticity. I is the moment of inertia. L is what we call the unsupported length of the member, right? That word right there, that unsupported word, is very, very critical for you to be able to understand what length we're talking about when we're talking about these compression members. So the unsupported length of the member, And then finally, we have this last variable, K, that we call the effective length factor. We will talk about those here in just a minute. They are just a factor that are based on some things that were about the column or the compression member that we're looking at, right? So pi squared EI over KL squared. We know the variables, we can plug them in, and we'll calculate a load, right? Also, if we also have a P critical, we are also going to have a critical stress. The critical stress just corresponds with the critical load, right? So the critical stress is just the critical load divided by the area of our member, okay? But if we don't know what the P critical load is, we can calculate the critical stress based on pi squared E divided by KL over R squared, where R is what we call the radius of gyration, and it is simply just the square root of I over A. So just taking the variables into different configurations, we see that we can calculate. We have basically the same equations, just in two different formats. Okay. I typically just always stick with the P critical equation, because if you can find P critical, you can easily, one more step, divide another number to find the critical stress, instead of having to do I and A square root, trying to figure out what this radius of gyration is. It's just easier, I think, to calculate P critical and just start there. Okay. So P critical, pi squared EI divided by KL squared. So going back to these K factors, right? These effective length factors, what we call K factors. These factors are determined by the support condition of the compression member. And basically what they represent is the length of the member between inflection points, right? So this will be easier to see in a picture diagram when we start drawing them here in just a second. But we need to be able to look at the geometry of our column, or not necessarily always a column, but compression member in general. And it's based on the support conditions. Is this column pinned at the top and pinned at the bottom? Or is this column more like a cantilever column, and it's got a fixed base and it's not supported at the top? You know, think of like a stop sign on the side of the road, right? That post gets driven into the ground and it's fixed at the ground, and there's no support at the top, right? So all these different support conditions for these columns will lead to different K factors. Now there's basically 4 of them that we need to be able to identify, and we'll just start with the first one. Okay, so I'm just going to draw these 4 different columns. The first one, if this is our column or our compression member, right, I'm just going to generically say column here. We have this column that is pinned at the top and it's pinned at the bottom, okay? If I were to draw the buckled shape of this column, so say there's an axial load pushing up and down onto this column, at some point that column's going to buckle if that load gets high enough. The buckled shape of a pin column will just make that column bow out, where we're going to draw the effective length. The effective length is the length of the column between inflection points. Okay, the inflection points is whether it's, I'm going to say this for the picture that I've drawn, whether the buckled shape is concave left or concave right, right? So when the direction of the bending, the direction of the bowing changes, that's an inflection point. So obviously on our pin condition, we don't have an inflection point. So what we say here is that our effective length, LE, is just equal to the length of the column, right? If this is the length of the column, right? Okay, so this is the pin condition. And since our inflection points, our effective length is equal to the length, our K factor just equals 1.0. Okay? Let's do another example, and I think this will start to make a little bit more sense once we do another one. So let's do a second column where instead of it being pinned at the top and pinned at the bottom, let's fix the bottom. Okay, fixed the bottom support, but yet we're going to let the top support still be pinned. Now you guys may recall from statics and being able to just think about what the restrictions on different types of supports are, is that pin supports only allow rotation at the support, right? They fix the member left and right, up and down, translation wise, but the member is allowed to rotate at the pin. Fixed supports, however, also restrict translation left, right, up, and down, but they also restrict rotation about the support. So this is a pin fix. I just write it in blue. A pin fix column. And if I were to draw the buckled shape of our column here, we know that at the top we can rotate some, but at some point we have to come back because the fixed support will not allow us to rotate at the base, right? So our buckled column essentially becomes shorter, and our point in between inflection points, because if you can see the curve down here at the bottom of this column is going to be concave to the right, I guess, on the picture that we've drawn. And then up here at the top of the column that we've just drawn, the buckled shape is concave to the left, right? So we have an inflection point somewhere about right here, in general. And we'll call this other inflection point up here at the top at the end of the column. This is now the effective length of our column, the point in between inflection points, and we call this L sub E. And through long derivations, what we're going to be able to figure out here is that L sub E is equal to 0.7 times the original length L. Okay, so if the entire length of the column from support to support is L, our effective length, the length in between the inflection points, is 0.7 L, or 70% of the original length. All right. So what this 0.7 L tells us then is that our K factor becomes 0.7. All right. Let's look at another condition. We got pin, we got pin fix. We've got two other popular conditions to investigate. The next one, let's look at maybe a fixed fix column. Okay. So here's my column, fixed at the bottom, and it's fixed at the top. Okay. Again, knowing how supports work, if this column were to buckle, if we were to apply a compressive load in such force that it causes this member to buckle, it's going to have that sudden lateral deflections. But again, the supports are fixed, so we're not allowed to rotate at the support. So what we get is something like this, where the buckled shape is going to start off nice and perpendicular at the supports, and then it's going to buckle one way and have the maximum lateral deflection there in the middle. So again, we have an inflection point here and an inflection point here, right? The inflection point is where it changes concavity, left or right. Again, through long differential equations and theoretical calculations that we're not going to bore you with in class, the effective length of this column, L sub E, the distance in between inflection points becomes 0.5 times the original length L, right? So I'm going to make that 0.5 a little better there. So 0.5 times L, the distance between the inflection points is 50% of the length. So this is a fixed column. And since L sub B is 0.5 L, again, we get this K factor now where it's 0.5. So K factor equals 0.5. So that's pin, fix, and now fix. Our last column that we're going to look at, our last support condition that we're going to look at, is a cantilever column, right? So we're going to have a column, and I'm going to draw this a little bit differently. I'm only going to draw it about half distance, okay? Okay, so this is L now. L is still the entire length of the column. And if we were to apply some compressive load onto this cantilevered column, the top is now unsupported, so it can rotate and translate, right? But the bottom still being fixed cannot rotate or translate. If we were to draw the buckled position of this column, it would look something like this. Okay, where it's nice and perpendicular and straight at the base, and then at some point it just goes off and it has some lateral deflection at the top of the column. Now again, at this point in time there has been no inflection point, and we're still actually ending out with a tangential slope of 0 at the base. Our theoretical K value comes from the derivation of our buckled shape continuing until it hits inflection points at the top and bottom of this hypothetical, bottom column, if you will, where our theoretical L sub E now is equal to 2 times L. Okay, so this is our cantilever column, and our effective length in between inflection points, it actually takes a distance of 2L to get to those inflection points. So our effective length is 2 times L, which means that our K factor becomes 2. Okay, so these, I'm not really expecting you guys to understand or be able to derive this kind of stuff. I'm just wanting you guys to, I want you to be able to recognize what the support conditions are for a column, whether it's pin or fix or cantilever or pin fixed. We're going to stick with these 4 support conditions. Be able to identify what the support condition is, and then tell me what the K factors are for that column. Okay, so let's also, what I also want to make a note of is, now that we know what K factors are and we know what their values are, let's take a look at our P critical equation once more and see if things kind of make sense to us for this equation. Okay, so let's look at the equation. P critical equals pi squared EI over KL squared. Obviously, the variables in the numerator, as they get bigger, our P critical gets bigger, and the variables in the denominator, as they get bigger, our P critical will get smaller, right? We all know how math works. So let's take a look at this. Let's just say I have a column of some unknown material. Does it make sense that if I increase the modulus of elasticity of the column, that our P critical will increase? I believe it should, right? Modulus elasticity, say, of steel is 29,000 KSI. Modulus elasticity of aluminum is a lower number. A steel column, I hate to use the word stronger, but if we're comparing apples to apples, if I have the same exact shape column, but one's made out of steel and one's made out of aluminum, the steel one is obviously going to be a whole lot stiffer, a whole lot stronger, right? And it's mainly due to the modulus of elasticity being higher. So higher the modulus of elasticity, the stiffer the column is. Obviously, the higher the buckling load will be, the harder I will have to push down on that column to get that column to buckle. Same thing with moment of inertia, right? Moment of inertia we defined in statics as the resistance of a shape to rotate, right? So basically, if a shape has a higher moment of inertia, the harder it is to bend, right? So if our sudden lateral deflections are dependent on bending, right? They've got to bow out. They actually have to, the columns will literally bend one way or the other. Our moment of inertia, if it's higher, it will be harder for that buckling load to all of a sudden bow out our columns. So the higher the moment of inertia, the higher the modulus elasticity, the better our buckling resistance for our column will be. And that makes sense. Obviously, too, we look at K and L on the denominator of our equation. Let's start with the length. If our column is a short little column, it will be very hard for that column to buckle. All right, so imagine we're going to go back to that paper clip that you straightened out, and you've got it between your fingers, and you're pushing on it, and you're trying to buckle the paper clip. Imagine that you can buckle it with X amount of force. Say it's 5 pounds is what it takes to buckle that little piece of paper clip. Well, what if you were to take that paper clip and cut it in half and only try and get half of that paper clip in between your fingers and try and get the same buckling effect out of that? You will find that it is much harder to buckle that little shorter piece of wire than it is to buckle the longer piece of wire. Intuitively, this might make sense to a lot of you, right? So the longer something is, the easier it is to get it to bow and to get it to bend out like that is under a compressive load. The shorter it is, the harder it is to buckle it. And then finally we come to our last variable, K, our effective length factors. The higher the K factor, the lower our critical load should be. So we look down here at our different K factors that we have. Our highest K factor is for the cantilever condition, right? So that makes sense. The highest K value gives us the lowest critical load. So our cantilever has the highest, and that makes sense that it has the lowest resistance to buckling because it is the least supported member that we have, right? It's only got supports on one side of the column, right? So if it's only got support on one side, it's not supported that well. It's going to take a whole lot less force to buckle that column than if say we had an identical column of the same length and size, but it's fixed at the top, which is our lowest K factor, right? So the lowest K factor gives us the strongest critical load that we can get based on support conditions, and that makes sense because a fixed column, if I'm fixed on the top and fixed on the bottom, that is as supported as it can get, right? So support conditions play a major factor into calculating our critical loads because our support conditions define our K values, which are one of the variables in the equation. So I'm going to stop rambling now about buckling. I've spent 20-something minutes here on the first page, but it's a very conceptual concept that you guys need to be able to see. And I hope at this point in time you guys are with me, you're following me, and that we all understand that buckling happens with compression members, and that the modulus, the moment of inertia, the length, and the K factors are the only variables that we have to look at. All right, so let's take a look at our first example. You know how we always start with a pretty simple example, so let's start with this one. We've got an A992 column, which is a steel column. It's got an unsupported length of 20 feet and it's pinned at both ends. Determine the critical load if the cross section of the column is as shown. All right, we've got this, square tube column. It's a 6 by 6 column with 1/4 inch wall thickness. So we know that our critical load, piece of critical, is what it's asking us to calculate. We know P critical is pi squared EI over KL quantity squared. Modulus of modulus of inertia, right? Modulus of elasticity, E, we know that, right? That's a material property. We've been given the material. It's A992 steel. Modulus is 29,000 KSI, right? 29,000 kips per square inch. Also, if you want to write it in PSI, that's 29 million PSI, right? Add an extra 3 zeros on it to convert the kips to pounds in the units, right? So 29,000 KSI or 29 million PSI. So we know E. I is the moment of inertia, right? And we're going to get that from the cross section. We're going to have to calculate that, and we'll do that here in a second. K, we've been given for this particular column. It says that it is pinned at both ends. So if we're pinned at both ends, that's a pin-pin column. K equals 1.0. Okay? And then finally, our last variable that we've been given is the length of our column, specifically the unsupported length of 20 feet. So we have 20 feet, which we need to make all of our units into the same units. I tend to like to keep my units in inches. So 20 feet times 12, that's what, 240 inches, right? So we're going to be there. So the last thing we need to do then is to calculate our moment of inertia I for a simple rectangle tube. This will be step 1. Inertia. I know when we're doing our statics review at the beginning of the semester, we probably would have broken this up into 4 shapes and added up and used the parallel axis theorem, and we would have done BH cubed over 12 plus AD squared for all 4 shapes and added it all together. There is a very simple trick for doing shapes like this that are symmetric and are rectangular, and all shapes coincide with the centroid of all the shapes coincide with the neutral axis, and it's to have a bigger square and a smaller square and subtract the smaller square from the bigger square. So if that doesn't make sense, maybe it will in formula and equation format here. So what I'm going to do is figure out the moment of inertia of the overall shape, the 6x6 shape, and then subtract out the moment of inertia of the 5.5 by 5.5 shape, because the 6x6 and the 5.5 by 5.5, those 2 shapes, the centroids of which will coincide at the centroid of the overall shape. So we can do this fairly easily. So the big shape is going to be 6 BH cubed over 12, and it's just 6 times 6 cubed over 12. We don't need to add in the AD squared term because our D term is going to go to 0. So now we're just going to subtract out the small square. So 5.5 times 5.5 cubed over 12. Again, don't need the AD squared term because the D term will go to 0. Just running our math out on this, we get our moment of inertia to become 31.74 inches to the 4th, right? And if you will take a look at this particular cross section of this tube, it doesn't really matter what we call IX or IY because it's completely symmetric about each of its orthogonal axes, right? So I'm just going to put here that this is the moment of inertia in the X and the moment of inertia in the Y, right? Doesn't matter which way we're looking at. And it does matter which way we look at it because we can always have buckling in different directions. If you can imagine that this sudden lateral deflection of these compressive members, right? We don't know which way it's going to go. It could go left, it could go right, it could go in and out of the page, it could go any which direction. We don't know which way it's going to buckle. It's just a sudden lateral deflection. So with this particular member, since our moment of inertia about both X and Y axes are same, what this really tells us is that we cannot accurately predict which way it will buckle. All right. So we've got E, I, K, and L now. We've got all the variables figured out. Let's just plug it into our equation and figure out what the critical load is. All right, so P sub critical is equal to pi squared, and Our next variable is the modulus of elasticity. Make sure that you guys are paying attention to your units right here. We've got a stress, we've got a force per area, right, for the modulus of elasticity. We've got length to the 4th power for the inertia. K value is unitless. Length is obviously a length, and it gets squared. So we need to make sure we use the same units for everything. So what I like to do, is just my personal preference, is to put everything in pounds and inches in those units, right? So if I've got something in force, I'm going to put that in as pounds. If I've got something as a length, I'm going to put it in as inches. If I got something in stress units, where it's a force per area, I'm going to put it into my equation as PSI. I like to use the pound and inch formulas units instead of the kip and inch units, or the kip and feet, or the pound and feet, right? It just, pick one, personal preference, stick with it. I like pounds and inches, okay? So modulus elasticity is 29,000 KSI, but like I said, I like to use pounds and inches. So I'm going to plug in 29 million PSI into my equation. Moment of inertia I, 31.74 inches to the 4th, right? All divided by KL squared, where K for this problem is 1.0, and the length of our column is 20 feet. Again, just putting that into inches so that our units will work out. We get 240 inches, and that term gets squared. So if you look at our units, we have PSI and inches to the 4th on the top. Those will cancel out to pound inches squared, and then we take that and divide it by inches squared from the denominator, and that just leaves us with pounds, right? So when we do our math here, the answer comes out in pounds, and it will come out to some 157,700 pounds. So just call it 157.7 kips. All right, that is our critical load, P critical. It's going to take 157,000 pounds to buckle this 20-foot steel column, 6x6 with 1/4 inch wall thickness. That's it's a pretty stout column. It can support quite a bit. Okay, so this is our first example on just basically coming up with a basic example on how to calculate P critical. So let's go to our second example, where we have to kind of figure out what the load is, right? So this time we're going to determine the maximum force P that can be applied to the handle so that member BC, right, this rod here, this rod BC, figure out the load P that will, the maximum force P so that rod BC doesn't buckle. BC is A36 steel, diameter 25 millimeters. Okay. So let's just take a look at the equation. Let's see what we've been given. So P critical is equal to E, or pi squared EI over KL squared. Modulus elasticity E. This is A36 steel. All steel has the same modulus of elasticity except for stainless steel. It's a little bit lower. A36 steel is 200 gigapascals in the metric units, right? Make sure you continue to decipher between metric and US units, right? It's not 29,000 KSI this time, it's 200 gigapascals. We need to calculate the moment of inertia for member BC. What about the K factor? Do we know the K factor for member BC? We do, right? Looking at the member, it is pinned at B and it is pinned at C. So our member is pin. So it's 1.0, right, for our K factor. And then finally, the length of our member, the unsupported length specifically of our member. We've got pin at B, pin at C. Our unsupported length is 800 millimeters. 0.8 meters, right? Good. So the only variable that we need in our critical equation is the moment of inertia. And this particular member BC, moment of inertia, the member has a diameter of 25 millimeters. So if you guys will recall that the moment of inertia of a circle, right, we don't do BH cubed over 12 for a circle, right? It is pi times r to the 4th over 4. So just plugging our numbers in. The radius for this is 12.5 millimeters. And that gets to the 4th power. So when we do our math here, you get 19,175 millimeters to the 4th power. So again, guys, we've got all of our variables figured out now. We can plug it into our P critical equation. Pi squared times E. When I'm dealing with metric units, I like to keep everything in the base units of meters and newtons. So 200 gigapascals becomes 200 times 10 to the 9th. Our moment of inertia is 19,175. I did not write this number out, but we need to move the decimal over 12 times. So we're going to get 19.175 times 10 to the negative 9th. Is that right? That'll be meters to the 4th. I'll write that in there so we understand. Meters to the 4th, right? So I'm converting millimeters to the 4th to meters to the 4th by dividing by 1,000 4 times. And then our K value is 1.0, and our length in meters in our base units is 0.8 meters, and we get all this squared. So the way we've done our numbers, the answer will come out in newtons, right? We had 200 times 10 to the 9th, that's pascals, so that's a newton per meter squared, multiplied by meters to the 4th gives us a newton meter squared, divided by meter squared gives us newtons. So we run our numbers out here, we get some 59,140 newtons, so call it 59.14 kilonewtons. Okay, that's P critical. But that P critical is not the maximum force P that can be applied to that handle, right? The critical load of member BC is just the force, specifically the internal force of the axial member, that if 59.14 kilonewtons gets developed inside of that rod, then the rod will buckle. But it doesn't necessarily coincide with the applied force P. So that's what we need to determine, is what force P will develop 59.14 kilonewtons in BC, right? That'll be the applied force P that causes member BC to buckle. And we just do this simply by statics, right? We're going to apply our principle of statics to figure out what this maximum force P is. And first off, all we have to do is draw a rigid body and some forces and some moments on it, and set the force in BC equal to 59.4 and back solve for P. So if you're looking at this, the easiest way to do this is to take the bent lever arm as the rigid body and draw it from there. So I'm going to do that down here. We're going to apply our statics to this problem, and we're going to have this. I'm going to have this member, where force P gets applied. This will be point A. This will be point B. Point A is a pin, right? So we'll have AX and AY that occur at that point. And then at point B, we will have the compressive force that's inside of member BC pushing back onto the lever handle. So if the force from rod BC pushes back onto the lever handle, it will be here. So this will be force BC. But we're going to set force BC equal to 59.14 kilonewtons because that's the buckling load in BC. And we're going to figure out what force P causes FBC to be equal to 59.14. So not trying to wail on the statics here too much, but all we have to do is take our moments about point A, set it equal to 0, and back solve for P. So if we do this, if we sum moments about point A, obviously AX and AY will cancel. What we'll get is a positive P times 350 millimeters, and then a negative 59.14 times that moment arm, which is 250 divided by square root 2, right? It's just cosine 45. And we're going to set that equal to 0. So one equation, one variable. Very simple here. P comes out to be 29.87 kilonewtons. Okay. So that is the answer to this problem. Nearly 30 kilonewtons worth of force, the P force, if it's 29.87 kilonewtons, it's going to develop 59.14 kilonewtons worth of internal axial force in our rod, and that is the maximum that P can be, because any more force from P in our rod will go above our buckling load, and the rod will buckle, which is not good. That's not what we're looking for. So that's this problem. Back solving into an allowable load so that one of our members does not become overstressed and buckle. I am going to leave this truss problem for your homework. Okay. For this problem here, we're going to determine the maximum force P on the truss so that member AB does not buckle. So member AB is a A36 steel member. It's got a diameter of 40, right? So if I know the material, I know the diameter, which means I know the inertia. I can look at it and tell the length. I can look at member AB and tell the support conditions, so I can figure out what my K value is. I can automatically on this problem go ahead and calculate the P critical for member AB with just a simple calculation of the inertia, right? So once you have that, we're going to set that value equal for the internal force of AB, and then back solve for an allowable force P. So I'm gonna leave this one for your homework. You guys take this one, and we'll continue on with our notes. I'm not wasting too much class time here going over repetitive problems. And actually, I believe this is where we're going to stop for today. Our next video, for when I'm out next Thursday, I'm going to cover these next two problems. These next two problems are a little bit different because we're going to start calculating the critical loads for members that are not symmetrical about their X and Y axis, meaning that the moment of inertia about the X is different from the moment of inertia about the Y. That'll be this problem. And then finally, the next problem, our unsupported links in the opposite directions will also be different. So I'm going to leave, these two problems here are a little bit more complicated. and are going to require a little bit more explanation. So I want you guys to understand the basics of buckling first. Let's do this problem for a homework, and I'll also give another problem or two in the homework assignments to be due, and then we'll do this problem either in class or in a video next week. I haven't quite made up my mind, but this will be it for today, and I will see you guys in class on Tuesday.